Welcome to Wildcat Science with Mrs. Haugo. This is Physical Science, Chapter 1 on Forces, and today we're going to be working on 1.3 Hooke's Law and Proportionality. So we are postponing our lab 1.2 weight in the spring scale, and we're going to jump ahead to 1.3. So please find your book, Force, Motion, and Energy, and open it up to page 6. So in experiment 1.2, weight in the spring scale, you can imagine making marks on a piece of masking tape to show how much a spring stretched with each increase in weight. So what we had were every group, you can imagine, would have a different amount of water, maybe 50 milliliters or 100 milliliters or 150 milliliters. And as you can imagine, those would stretch different amounts. So if you use the weight of 150 milliliters of water as your unit of weight, your results would have been similar to those in this table, which shows the number of weight units added to each step. So each one was 150 milliliters of water, and each time you added 150 milliliters of water, our spring would stretch 7.5 millimeters. So there is another way to predict or present these results. Recall that the 0 mark was set at the position of the indicator when the bottle was empty. When 1 unit of weight was added, the string stretched 7.5 millimeters. When the second unit was added, the string stretched an additional 7.5 millimeters. Hence, it was a total stretch of 15.0 millimeters. Continuing in this way, we can replace table 1.1 with a table that shows the total stretch produced by the total weight at each stage of the experiment. So looking at total weight in our special water weight unit of 0, 1, 2, 3, 4, and 5 additions of 150 milliliters of water, we would have a stretch of 0, 7.5, 15, 22.9, 30.2, and 37.7 millimeters on our spring. The data in table 1.2 can also be displayed on a graph, which is figure 1.3. The graph is clearly a straight line through the origin. All points in the graph have a common property. The ratio of their vertical coordinate to their horizontal coordinate is constant. For example, for a total weight of 1 special water weight unit, the total stretch is 7.5 millimeters. This gives a ratio of 7.5 millimeters over 1 special water weight unit equals 7.5 millimeters over 1 special water weight unit. So please take a moment and do a digital post-it note. Great, let's see that on the graph. We can see in the graph it's stretch versus weight, and our total stretch is each addition of a special water weight unit. So when we add 1 unit of water weight, which is about the weight of 150 milliliters of water, it stretches 7.5 millimeters. Total stretch versus total weight. So for a total weight of 2.4 special units, the stretch is 18 millimeters. Again, we find the ratio of 18 millimeters over 2.4 special water weight units is 7.5 millimeters per special unit, which is the same as up here. Coincidence? No. So let's find that on our graph. So 2.4, we go up, and then we find that it is 18. There we go, 18. So when the ratio between two variables is constant, one variable equals the constant value times the other variable. For the graph in figure 1.3, the relationship between the variables can be expressed as stretch in millimeters is equal to 7.5 millimeters per special unit times the weight in special units. So let's come down and look at the graph a little bit more. Great, please do a digital post-it note. So such a relationship is called a proportionality, and the constant is called the proportionality constant. There's a broader discussion in Appendix 1. Note that when two variables in a proportionality have different units, the unit of the proportionality constant is the ratio of the two units. If the two variables have the same unit, the units cancel and the proportionality constant is simply a number. It is a pure number with no unit. The proportionality constant between the stretch of a spring and the force acting on it is called Hooke's law. This law, like other laws of nature, is a generalization based on measurements. Thus, we can have confidence in the law only in the range in which it has been tested. The design of your spring scale prevents you from causing permanent damage to the spring by pulling so hard that you would stretch it beyond the range in which Hooke's law applies. So our spring scales, Hooke's law will definitely work with our spring scales. So please take a moment and do a digital post-it note. Okay, we're going to have Professor Mack tell us a little bit more about spring scales and stretch and Hooke's law.
Hello, my name is Professor Mack. Welcome to my laboratory. Come and have a look at this. This is a Newton spring balance, and it's a device which enables us to measure force. It has a fixed end, which is used to support the balance, and a free end, which moves. So how does a spring balance measure force? Well, as my hand pulls the free end, it stretches a spring, and in doing so, I can feel the spring applying a restoring force to my hand. In order to maintain the stretch of the spring, I have to apply a force equal and in the opposite direction to the restoring force generated by the spring. As I increase the stretch of the spring, I have to apply a larger force, and as I do so, the spring applies an equal but opposite larger balancing force to my hand. So in a spring balance, there is a relationship between spring extension and applied force, and therefore by measuring spring extension, we can measure applied force. In order to do this, we have to know the precise relationship between spring extension and applied force, and to establish this relationship, we need to conduct an experiment. So as part of our experiment, we need to measure spring extension. You can see on the spring balance we have a scale which measures the extension of the spring in millimeters. We see that we have zero extension of the spring, as shown on the scale, when zero force is applied to the end of the spring balance. In order to establish the relationship between force and spring extension, we will plot these on a graph. The vertical axis will be the applied force F in newtons, and the horizontal axis the spring extension X in millimeters. The first point for us to plot on the graph is zero extension for zero applied force. If we now apply a force of 5 newtons to the spring balance by adding this mass, which has a weight of 5 newtons, we see that the spring extends by 50 millimeters. When the mass comes to rest, the applied force, which is a gravity force of 5 newtons vertically down, is being balanced by the restoring force of the spring, which is 5 newtons vertically up. So let's plot this point. That is 50 millimeters extension for an applied force of 5 newtons. Now let's add another 5 newtons to the spring. Can you guess how much it will extend? as you can see, it has extended another 50 millimeters, so that the total extension is 100 millimeters for a total force of 10 newtons applied to the spring. So let's also plot this point. Now you can see that the 3 points lie on a straight line. This is very important, as it is the principle on which the spring balance works. It simply says that the relationship between force and extension is linear, and that is why the spring extended by the same amount each time we added 5 newtons force. This linear relationship between force and extension is known as Hooke's law, after Robert Hooke, who discovered it in 1660. As Hooke's law is a straight line, we may express this mathematically as the applied force F equals a constant K times the spring extension X. The constant K is known as a spring constant and is the ratio between the change in spring force for a change in spring extension. Mathematically, it is the slope of the line in the graph, and it is a unique property of each spring. So you can calculate the spring constant by calculating the slope of the line. To do this for our spring balance, we divide 5 newtons force by 50 millimeters extension, which gives a spring constant K equal to 0.1 newtons per millimeter extension. This means that we can calculate the force on the spring balance using Hooke's law in the form force F equals 0.1 times the spring extension X. Now that we know the relationship between force and spring extension, we may use this to calculate the force applied for a measured value of spring extension. You can see in the spring balance we have an object of unknown weight. The object applies a force to the spring balance due to its weight. So let's use Hooke's law to see if we can predict the weight of the object. The spring balance shows the extension of the spring is 70 millimeters. So using Hooke's law for our spring balance, we predict that the force applied, which is the weight of the object, is 0.1 times 70 millimeters, which gives a force of 7 newtons. So let's see what the weight of the object is. Aha! It is just what we predicted. The weight of the object is applying a force of 7 newtons to the spring balance. Well, there you have Hooke's law and the Newton spring balance. I hope you enjoyed learning about them. So from me, Professor Mac, until next time, all the best. Bye.
Okay, well, hopefully you learned quite a bit from Professor Mac. Tomorrow, we're going to be taking notes on Chapter 1.3 and then trying our hand at Hooke's Law with some questions. All right, see you then. Bye.